able to present now. So do you all see my screen? I guess so. So once again, you see my name here, Frederick Linz. I'm the CEO of Exostiv Labs. Shall we start now? Yes? Absolutely. Yes. So our company is based in Belgium, so Western Europe, very close to Turkey. And our main partner in Turkey, or only partner in Turkey is CDT, of course. And thank you for organizing this presentation. To give you a little bit of feedback about, of background about our company, we have always cared about FPGAs. But what we are doing now, I mean, providing EDA tools for verifying and debugging FPGAs is something that helped us busy since 2015 or so. And this is the main activity we have. This is the sole activity we have. And so it starts from the point and the concept that as originally FPGA designers ourselves, we have always thought that designing FPGAs requires the right mix of tools and methodologies. And of course, we do believe that simulation is a must, and you can extend it with code coverage and many other tools. However, this said, we have seen that with the increasing complexity of FPGAs, be from Xilinx or Intel, still we strongly believe that going to hardware to run some testing at least, or debugging or verification task is still necessary, just because, well, software is really fine and gives you have a lot of qualities, but when you go to hardware, this is when you really confront your system to the reality, and this is when you can detect still things. And so we have wanted to bring some tools to what was available on the market yet, and what you see here must be something that is very familiar to you. That is debugging an FPGA with a JTAG-based logic analyzer, well, in short, ChipScope or Xilinx ILA from Xilinx, or Signal Tap from Altera Intel. And so this tool has always been very useful. So inserting an IP in an FPGA, sampling some nodes into a memory and read back this memory has always provided quite some visibility into the FPGA. But if you look at the following slide and say that this is when you start, you see there is a timeline. That arrow is a timeline. Maybe I can use some ink over here. So this is when you start to your circuits, and this is time. Well, say that you are putting your system in the real environment and looking for a bug or some event here. With the capacity of the memory you have in a FPGA, it reduces to using a very small, how do I erase that? Yes, erase all ink. It reduces to using a very small observation window that is of this slide, of this size, sorry, to try to find something that happens unexpectedly. And so when you have such an observation window, so what I call the observation window is what's defined by the quantity of memory you are able to use for storing traces. When you have such a small observation window, then you are reduced to basically shooting in the dark and try to capture over and over again data until you find the bug by chance. We have wanted to take that paradigm, to take that same structure with Exostiv. And if you have to remember just one slide about what I'm presenting today, it would be this one. So this gives you really the overview of what Exostiv is. So you have your target FPGA over here, and For Exostiv 2, you need to insert a piece of IP into the FPGA, which eventually is connected to some nodes that you are going to sample. But unlike a JTAG-based tool, we don't put the main memory facility for the traces inside the chip but outside of it, and we use a high bandwidth channel to stream the data to this large RAM. And doing so, not only we can repeatedly collect that observation window, and you see we fill in this memory and then store it into the large external memory. And so doing so, even if it's interrupted here, gives you a better chance to capture what you want to see, so the bug can be seen. But also, if you have got a sufficient bandwidth over this link, you can imagine using this RAM as an elastic buffer and capture the data continuously. And actually, Exostiv as a tool can work in both ways, depending on the circumstances and the capacity of your link. Both ways of working, this one and this one, can be very useful because interrupting the capture lets you filter also the data that you don't need. And using this way of working until the memory here is full can give you a better overview over time. We have examples of customers sampling IPs during 1 hour or 1 day by small chunk that they repeat. Whereas with the original way of doing, once you have captured one time the RAM that's inside your FPGA, you're done. So very useful way. And another useful way would be to give a better overview and continuous overview of what's going on inside your FPGA, maybe on a more reduced data set, because of course you need to be able to stream that to the memory. Everything of this is going to be more obvious when I do the demonstration. This is the clear overview on the product itself. So Exostiv as a product, it is what you see here on the slide. It's composed of 3 parts, so an application that runs on a workstation, a probe, and that's the orange box that I showed you on my cam earlier. And this application is used for inserting a core inside the FPGA. So 2 things basically, configuring and inserting that core inside your target FPGA. And in a later step, the same application is used for controlling this box and run some captures. So some numbers here, you see that the main memory is placed inside the probe and you have 8 GB of trace. That has to be compared to what you are used to having with JTAG tools, where basically the limitation is what you can afford from inside the FPGA. And this is a simple example. We have captured 100 bits at 250 megahertz sampling, and even reserving 40 kilobytes of memory in the FPGA, all you could see from the FPGA was 13 microseconds. Whereas with Exostiv and not even using that much memory, we've been able to capture 3 seconds continuously. So that memory is a game changer. 8 GB instead of a few bytes of kilobytes means that you can reach new kinds of capture scenarios and explore your FPGA during much longer times or during capture that span over longer times. From inside the FPGA, well, there is no real magic there. You need some resources to reach your nodes, the nodes that you wish to observe and sample them. In our case, we can have up to what we call 16 capture units. So it means that you can view up to 16 different clock domains altogether. And each capture unit can be connected to up to 2K nodes. Well, that does not mean that you will always look at so many nodes. We have clearly cases where a few hundreds of them are clearly sufficient, especially if you look at them continuously. So Those trade-offs are things that we can discuss later. As for the bandwidth between the IP and the probe, we implement something that uses the transceivers, so the SerDes of the FPGA, at currently up to 4 × 12 gigabit per second. So it means that for using Exostiv, you need an FPGA with transceivers, and you need at least one transceiver available for Exostiv. Regarding the physical characteristics of our probe, you see that we connect to the FPGA through 2 kinds of connectors, and basically you can use many types of connectors. So we have an adapter that goes over FMC, HPC or LPC, so that large connector that's available on most design kits, and you see that there are some other adapters here that are able to provide the connectivity with the probe. So this is our adapter with a special small connector that uses HDMI. It's not HDMI, it's a custom connector. And those are examples where we have SFP or QSFP connectors. So SFP or QSFP connectors are for using those bays, and the HDMI is for this one. Direct connection with SFP or QSFP cables such as these are very common, and this is what I'm using today. And for those who design their own FPGA board, we have defined a custom low footprint connector that you can add to your PCB with a very little use of footprint on the PCB. And you see this is this very tiny micro HDMI connector on which we can route up to 4 transceivers. So physically, you see some pictures of what it can give. This is the setup that I'm using. So I'm using this QSFP connectivity with the probe. In this case, on the picture, you also see our FMC adapter for such design kit. This is an example of board where we have a small FPGA, an Arctic 7 FPGA with 4 transceivers, and we have added that small connector. You see it's very small. It's the size of a micro USB connector, and the cabling here, the blue cable to the probe. And this is a much bigger system. This is basically a system for prototyping ASICs where we have plug-in boards, and you see they've added the plug-in board with QSFP here connected to the probe once again. So if you really wonder where you could find a board that's commercially available and available out of the box for using with Exostiv, you can check our website. There is in support FPGA board, you find a lot of numbers of boards that you could basically use out of the box without adapting, without adapters, or with an adapter that we can supply. And also, if you want to use a custom connector on your board, in the support and documentation section, you can find the connecting guide. So everything will be supplied through CDT, of course, and but you can have a look at exostivlabs.com as well. So we've spoken about the capabilities, we've spoken about how to connect the probe to your board, and now we can speak about how you insert an IP inside your FPGA. So basically we have 2 flows. We have the first flow, what we call the netlist or automatic flow, and that's available for Xilinx FPGA only. And in that flow, you are going to synthesize your own design, and then from there, link to Exostiv, because as you will see, I will demonstrate this, we have an integration with Vivado, and this is where you're going to define and insert our IP. And this will be inserted automatically and interactively. We have another flow where we generate our IP from our software, and we provide it to you as a black box, and you are able, with a template, to simply modify your RTL code, so Verilog or VHDL, to insert Exostiv. And so in this case, it is a semi-automatic flow, so the IP is generated automatically, but the insertion requires some editing of your code. And this flow is available for both Xilinx and Intel FPGA. I will come back on this later, but that gives you the the overview of what you are really inserting inside your FPGA when you are using Exostiv. You see that that's your design. We have up to 16 such capture units connected to some data from your design, which can be also multiplexed. And on the other end, we have the link part, that is the transceivers, that's the link with the IP. And we have that downstream channel that allows us to change things like the trigger or some settings on the fly without having to recompile your FPGA. So I'm going to get back on this later, with the demonstration. So beyond debug is a more kind of advanced use of Exostiv. Just to mention it, when people think about Exostiv, they can first think about a replacer for JTAG-based logic analyzer, with much more visibility. Get beyond JTAG-based logic analyzer and have a gigabyte of visibility instead of kilobytes. So that's a huge step forward. You have to know that we have some customers using Exostiv really as a recorder for collecting input vectors for some IPs in a design under test and replay them into the simulation. And so that's the other way around. We use Exostiv really to enhance the cycles used for simulation. So just to mention it, there is a case online and we can provide more information about that later as well. So other features, Exostiv can be used with scripting, so you can automate the tasks. And well, we have customers using that extensively to run automatic testing during who nice. That makes of Exostiv more a testing tool rather than a pure debug tool. And this is more or less where I'm going to stop bothering you with PowerPoints and switch over to the demonstration. But perhaps first I can take some questions. Are there any questions? No. No so far. All right, don't hesitate to do that. So I'm going to run the full flow of Exostiv, inserting such an IP inside of the FPGA that I have next to me. And this is basically what we are going to demonstrate today. So you see that on my board I've got a Xilinx Vertex UltraScale FPGA. And in this FPGA we have some existing data generators. So we have a counter, a random generator, and sine wave on 16-bit, and we have some video interface already generating some video frames. And we are going to define an IP that's over here, the orange box, with 3 capture units, 1, 2, and 3. And you see that in those capture units, we will have a 1K buffer or 2K buffer. That's important because for the demonstration, that will give you some comparison points with what you maybe could be doing with a JTAG-based logic analyzer. And so we're going to insert an IP into the FPGA that's establishing a connection with the probe over 4 links here and a total bandwidth of 50 gigabit per second. Discount ink. So the first thing I need to have is a design loaded in Vivado. This is a Xilinx board, and you see that I've already loaded my design after synthesis. So it's in Vivado. And how do I do that? I need my, please hold on. Yes, and I'm going to start my application now. So this is Exostiv dashboard software. So I'm going to recall some settings here so that you can see what a project looks like in Exostiv dashboard. And as you can see, we have a flow on the top of this window. So you see there are multiple steps for inserting and using Exostiv. So the first 3 steps over here are used for defining the exhaustive IP that's inserted inside the target FPGA and inserting it inside of it. And so the first step that we are going to go through is the link configuration. The link configuration is all about specifying the characteristics of your target board and the target FPGA that you are using. So in my case, it's already selected for you, but you see, it's all about defining which FPGA, which target FPGA we are using. So we have a Vertex UltraScale FPGA, and that part, you just have to select it. So you see that inside of our software, we have a library of FPGA parts. And so we cover Xilinx FPGAs Series 7, so Vertex 7, Kintex 7, Arctic 7, UltraScale devices as well, Kintex and Vertex, and UltraScale Plus devices. Zinc devices too, so Zinc 7000 and Zinc UltraScale Plus. So all those parts. For Intel FPGA, we cover Series 10 only, so ARIA 10, Straight-X 10, and very soon Cyclone 10, if yes, as well. So once you have selected your target part, what you need to specify is where you are going to connect the probe. So it's basically selecting the FPGA bank and the location of the transceivers over here. So what you see here are the reference of the pins. So in my case, I'm going to connect Exostiv to bank 127 because this is where I've got my connector on the board, and I'm going to enable all 4 links on the same bank. Finally, if you wish to generate a traffic onto the transceivers, you need a reference clock for them, and that clock also enters the FPGA at specific sites, and so you need to select the pin where that clock enters and tell the tool at which frequency it ticks. So that's basically reflecting what you have on your board. And in my case, doing that, I've got 4 links running at 12.5 gigabit per second. This is the data rate I've selected here, which makes 50 gigabit per second. For the rest, what you have here is the selection of the connector on the front panel of the probe. And we also need to use one of the transceivers as a downstream channel. So we use that as a full duplex facility, and we select this one. And these are some settings for the downstream link rate, which I won't enter into detail. So once you have done this, you have basically defined what you have here in the link part of the transceivers. Sorry for that. So I'm going to close that. So the link part, so the transceivers, I've got the transceiver reference clock, everything's defined here. And what we are going now to define is the logic that really samples the data from your FPGA. So we are going to tell to the tool how many capture units and what nodes it has to sample. So once again, we switch to capture configuration here. And you see that on the left-hand side, we have a panel to define the capture units that you want to have in this IP. So it's just double-clicking. And what you have here is basically the definition of your data groups. So what are data groups? So if you see here, you can multiplex up to 16 different data groups in front of your capture unit. So that defining multiple data groups actually defines a mux that you can select later on in such a way that you can reach a lot of nodes from your FPGA with the same capture unit. The only thing is that you are going to look at one data group at a time only. So you can define up to 16 such capture units, and for each capture unit, 16 data groups. And for each capture unit, you have some settings that you need to define. You have some ability to define a trigger unit that's sensitive on level edge or level edges and comparisons. Of course, making it more complex will use more resources in your FPGA. You have an even counter as well if you say you want to react on the 10th occurrence of a trigger, well, there is a counter for that. And there is also an optional storage qualification unit, which means that you can basically filter the data upfront in the IP on a logic condition. I will demonstrate that later. Most importantly, you need some buffering inside the capture unit. And you see that for the system and the video capture unit, I've got a 1K buffer here. So that's a temporary buffer for the traces before we send them to the probe. That's it. So once you have that, you have a capture unit, but you don't have a connectivity with some nodes yet. So here you see that in my project, I already have some nodes from the design that are connected, and I'm going to show you how we do that. So I'm switching to Vivado now, and you see that I remind you that I've got my design loaded after synthesis, and here you see we have added a button, and that button helps us to establish a connectivity between Vivado and our tool. So that's a kind of integration. And what can we do with this? Well, we can basically browse the design that's loaded in Vivado and select the nodes that we wish to observe from it. Also with some filtering capability, so we can filter on the mark debug. You can put some filters on the names as well. You can search throughout the RK and so on. And basically what you are going to do is browse your design and say, look, I want a connectivity with that or this node, and you are going to put them on the right and make a list. So you are going to do that. We are going to do that for all the data sets we have. You see, we have some data already connected to them. And once you have done that, you have fully defined your IP, because we have the link, we have the capture units. For each capture unit, last thing you need to specify the clock. For the capture unit, that's the same story. You are going to select it over from the design under test. You see, wait, I'm going to change some feature. Yes, you see, I only see the clocks in the design, because basically you will have to sample the data that's here with some sampling clock in the capture unit. So that's something you need. So once you have done that, your IP is fully defined, and you can switch over to this step, which is basically an automatic step. And during that insertion, we are going to generate our IP. So here, over here, yeah, generating memory, generating transceiver, synthesizing debug core, and then insert it inside your own design automatically. And then it is going to connect the nodes that you have selected, generate some constraints and implement the design until you have a bitstream. So that whole process here in this case uses Xilinx Vivado interactively from the tool, and you don't need to interact with it. It's fully automatic. And at the end of this process, what you have is a bitstream that's basically your design that's instrumented with some IP generated by the Exostiv dashboard. So I'm not going to run this because, well, it requires a place and route, so we would have to wait until it has finished. So it's a one button that says, okay, I'm running it all. And we are now at the step where we have already generated the bitstream, and I'm going to load it into my board. So I'm turning on my board and probe. And if you don't believe me, I'm going to put that cam on. Yes, hello. And so you see that I've turned on my board over here and my probe as well. And so I've got my JTAG cable here connected to my machine, which I'm going to use to load the bitstream inside the target board, Fpga here. And then after that, I'm going to establish a connection with this IP over that cable. So I'm going to stop sharing my video because it's basically here. I'm going to open my hardware manager and load my bitstream inside of the Fpga. So that's Vertex Ultrascale, program device, and that's this one. So now my yes, when it's finished, my IP is, my design is loaded inside the target FPGA, and I'm going to drag this, clear that, and connect my probe. So when I do that, I attempt to connect to the probe that's connected over USB to my PC, and then it is going to establish a connection with the IP that's loaded into the target design. And you see that there is a whole negotiation first. So we detect the probe, it has 8 GB of memory, that's a version of firmware. But the first thing is it connects the probe to the PC, and then it tries to connect to the IP and establish a connection. So it says that the downstream link is aligned, the QPLL are locked, it has detected 4 links and so on, and it runs a quality test. And you see that everything turned green here, which means basically that we are up, ready for up and running. So I'm switching to this screen here. So please don't pay too much attention to this, because these are waves that I've already collected before. So you see we have a tab per capture unit. So when we have system video and video extended tab, it basically reflects what we have here, system video and video extended, that are the capture units that you have defined in the IP. And I'm going, if you remember, we have a 1K buffer in one of those capture units. I'm going to show you what 1K buffer is, because basically, if you collect exactly the quantity of data that you have in that FIFO, you basically look at what you would see with a JTAG-based logic analyzer and exactly the same footprint in logic and memory. So, I'm taking the sine wave, for instance. I'm going to run one burst here, and I'm collecting 1K. So, you see that we have collected some waves here, and once again, this would be what you could see with a JTAG-based tool, not with Exostiv exactly, but that gives you a comparison point. You see that we have 16 bits toggling, and when we represent them as an analog wave, we have a sine wave. And we have tuned that sine wave so that 1024 samples exactly matches one period of that sine wave, so that you have a visual point. So this is what you would see with chipscope, Xilinx ILA or signal tap, and the same footprint in memory. And of course, we can do much more with Exostiv. So when I change a control sign, I say, look, I want to capture one time, I don't know, 2,000 nodes, 20,000, 200,000, 2 million samples, let's say, and run it. So here, we have captured not 1K, but 2 million samples. And when you have a look at the waves, of course, that's the general view with 2 million samples, but we have that same repeating pattern. You see the sine wave evolving. So instead of looking at this, we are looking at much more data. And in the very start of my presentation, I explained to you that, for instance, when you are looking at finding an event that you can't simulate, or that's random and that's only happening when you put your real system on. That was basically, sorry, that slide, yes, with this little guy. So sorry, yes. When you're looking at finding something that's not, you can't put a trigger on, well, having a small observation window, it can't help you very much. Whereas when you use a very large observation window, then you are certain to have captured the event that you are looking at. And in my case, I can tell you that we have inserted a random bug in that data stream. And so we are going to look after it. And you see here, I've got exactly here, I already have found it. So that's really random. We've put it on purpose, but that gives you basically the value of it. If you were to look at and look after that event that happened randomly with such a small observation window, then you would need to run your capture over and over again, maybe during weeks before you find that. Whereas with such a large recording from inside the chip, then you have it all in your recording, and you can find it afterwards by post-processing the data. Of course, in my case, it's very visual. If you zoom out, that's really for the example, because I already see another one over here because I'm trained to find them. But it must not be visual, of course. You can export all your waves to a database. You are not forced to use a waveform viewer, of course. So you can basically collect the database as a raw data to your PC or your workstation and post-process it with some algorithm for analyzing the data. So that's the value of the tool. Oh, sorry about that. That's the value of the tool as a tool that provides much more visibility than what's usually available for FPGAs. But that's not all, and I would like to demonstrate something else here. You see, I've switched over to the video capture unit. So basically, we are connected to a video stream over here, and if you look at it, we have a blanking here, vertical blanking, a line counter, a start of frame, so that marks the beginning of the frame, and we have the red, green, and blue compounds. If I represent them as analog here, you see we have some evolving ramp generated in the FPGA. So, and that's a real case that we have run into with one customer. That customer was looking at an event. He was designing video equipment, digital projector, and he knew he had a bug in the stream, but that bug happened once in a while during a 2-hour movie. And as you know, for video equipment, or don't know, we have the payload, of course, that could be interesting, but also all the ancillary data, all the control data of the flow, like what happens in the blanking and so on, is very important to keep the right stream. And with Exostiv, we've succeeded in capturing the beginning of each frame during the 2-hour movie, something he was really unable to do with another tool. So I'm going to show you that to show you the capability of the tool. So I've selected my video capture unit and the SDI data group, and I'd like to put a trigger on the start of frame falling edge. So I'm defining that. And then for the next 200 frames, so I define 200 captures, I will like to capture 41,000 samples. And I'd like to position my trigger somewhere, I don't know, in the middle. So you see, I say that my trigger positioning in each capture would be at a 22,000 sample. And when I do that, pay attention to this progress bar over here, because it is really going to wait for the next trigger, next start of frame, capture data, wait, and then wait until it encounters a trigger. And you see that in real time. So as I speak, the tool will capture data. So it means that from the start to the end of the capture, you have a few seconds, a few tenths of seconds, which is something you cannot do with a JTAG-based tool. So I'm going to run the capture. You see we have capturing as I speak, and we have captured 100, 200 frames now. And this is the post-processing of the data for the waves. So I need an encoding for the waves. And there I've got my waves. And you see that if I enlarge this, I've got 200 captures. If I zoom in, I've got that gray and black and gray area, which means that it is one capture. Each of them is a capture, and between them we have stopped capturing. And each of them is numbered. You see the number on the trigger here, and as a trigger on the event that I have defined, which is basically, the falling edge of the starter frame. And the positioning is right. If I zoom out, hold on, zoom out. So I've got something like 20,000 samples before the trigger and the rest after it. So in a stream, you will want to use the triggering as well, because you will want to make the most of that bandwidth you have over the transceivers. To do that, you can also use the data qualification. So this is something that says, hey, I only want to capture the data when one condition is true. And in my case, say that you are only interested in line 2e in hexadecimal for the data stream. You can put that condition over here. And I'm going to reduce that and capture only what's available in the stream when that condition is true. And doing that, you really filter out your data. You see, I've captured data, but the condition is always true. So what you are looking here is only the data that's happening during a wider condition, so in line 2e in my stream. And that's really useful. So these are the basic capabilities of the tool. We can, of course, have other things like auto-exporting the waves to CSV, VCD, or other things. You can have more complex data qualification and trigger conditions, including with a trigger counter. You can also use one capture unit to trigger the other one, so that gives you some sequence there. So that's really a tool that can give you a lot of visibility into your Fpga and speed up your testing, debugging, and verification. So I'm basically done with this. I would like to thank you for your attention, of course. You need to know that we are very much dedicating to making that solution evolve. We have launched it in 2016 around, and since then we have released up to 3 to 4 new software versions every year with new features. And we are going forward with more series, that is more powerful probes with more bandwidth, modular things that are more fitted for testing in the production or deployment or the data center, have multi-user hardware. So that's a little early to speak about that now. However, what's available today is EP 6000 with 6 gig probes and 12,000 with 12 gig probe. CDT can absolutely inform you about this all. And I would like to thank you for your attention. This is my email and the website where you can find a lot of information. And of course, you can locally in Turkey contact CDT for any information about this. Thank you very much for your attention. And I give the word to